Hi, I'm Jessica Chellino. I'm a PhD candidate at the University of Florida, and today I'll be talking about work I've done with Zach Slepian, John Minhu, and Alessandro Greco on developing a generating function for the isotropic basis functions that we use to parameterize endpoint correlation functions. I'll begin by going through a brief overview of endpoint correlation functions and how they can be used to search for parity violation. Then a majority of my talk will focus on how we developed a generating function for these basis functions, and I'll conclude by explaining how this generating function can enable a faster NPCF algorithm on the CPU. First, let's start with an overview of endpoint correlation functions. NPCFs tell you about the excess galaxy clustering above what you would expect in a random distribution. So the 2PCF, for example, you have 2 points or 2 galaxies separated by a distance r, and the 2PCF tells you about the excess of galaxy pairs above the pairs you would expect given a random distribution of galaxies. The 3PCF is similar, where you have a triplet of galaxies. You choose one as a primary and measure the side lanes r1 and r2 out to the other 2 galaxies in the triplet. The 4PCF is similar to that as well, where you have 4 galaxies or a tetrahedron formed out of galaxies. Choose one as a primary and measure the side lanes out to the other 3 galaxies. NPCFs have a lot of uses in cosmology, but recently the 4PCF has been used to try to search for parity violation in large-scale structure. If we assume cosmological isotropy, we have to average over rotations, and that means that the only way we can see a parity transformation or look for parity violation is by looking at three-dimensional shapes. And the simplest 3D shape is a tetrahedron, which means that the lowest order correlation function we can use to search for parity violation is the 4PCF. If we come down to this diagram, we have a quadruplet of galaxies forming a tetrahedron. If we assume that R1 is the shortest side length and R3 is the longest, we can define the handedness of a tetrahedron by the direction you travel going from the shortest to the longest side length, so R1 to R3. This tetrahedron has a clockwise handedness. And now if we imagine putting a mirror right here and reflecting the tetrahedron in it, that's similar to what we see when we look for parity transformations, we would end up with this tetrahedron on the right. And this tetrahedron has a counterclockwise handedness. So we can see that the handedness of a tetrahedron flips under a parity transformation, and by tracking the handedness of tetrahedra in the 4PCF, we can search for parity violation in large-scale structure. Now, how do we actually measure the 4PCF? We use what we call isotropic basis functions, which are functions that are rotationally invariant under a simultaneous rotation of all of their unit vector arguments. And these basis functions are composed of spherical harmonics and the Clebsch-Gordan coefficients or Wigner symbols. Now, these isotropic basis functions can have even or odd parity, so we can decompose the 4PCF into even and odd modes using these basis functions. The odd modes are sensitive to parity transformations, so they are really the important modes that we want to look at if we're searching for parity violation. Now, this is all old work, so what have we actually recently done with these isotropic basis functions? Well, we've come up with a generating function for these basis functions to obtain them in Cartesian form. But before I go into that, I want to just briefly review what a generating function is. A generating function allows you to write out a sequence where you can pick out certain terms. So a common example is from E&M, where you have the multiple expansion of a potential between 2 points R1 and R2. And that's what's being shown in this equation here. So if we expand the left side, the 1 over R1 minus R2, we get the right side, where this LL is a Legendre polynomial. So the left side here is the generating function for Legendre polynomials. Now, the Legendre polynomial has an argument that's the dot product of 2 unit vectors, so it's invariant under rotations. So motivated by this, we wanted to develop a generating function for the isotropic basis functions, which can have arguments of more than 2 unit vectors. The generating function we found, if you expand it in a power series, the angular part is the isotropic basis function. And This is useful because the isotropic functions are typically represented in spherical harmonics, but if we use our generating function, we're able to get Cartesian representations for them in terms of dot and cross products of the unit vector arguments. So these are just examples of the isotropic basis functions for n equals 2, 3, and 4 in the common spherical harmonic representation. So you can see that for each argument of the function, there is a spherical harmonic with that unit vector argument. Now, these spherical harmonics have associated angular momenta L and projective quantum numbers m. If we go to n equals 3 or higher, we see these Wigner 3J symbols, which couple the angular momentum together. So what our generating function does is allows us to get these isotropic functions in Cartesian forms, which are easier to work with and more easily interpretable. So now let's go through how we actually found the generating function for the isotropic basis functions. Let's suppose that we have some vector capital R, which is composed of vectors little r. And let's also say that there's a momentum p dual to r. And p doesn't really have to be a momentum, it could be some other dummy variable. Now, if we have the quantity e to the I p dot r, we can use the plane wave expansion to write that out. But what we're going to do is the plane wave expansion two different ways and set the expressions equal to each other. So I'm going to go through that on the following slides. And where we have a sum over the angular momentum L, the sum will range from 0 to infinity. And where we sum over the corresponding projective quantum number m, the sum will be from minus L to plus L. Okay, so let's take the quantity e to the ip dot r and use the plane wave expansion on it. We get this expression where we have a spherical Bessel function and two spherical harmonics. Now, if we first factor this exponential into a product of exponentials and then use the plane wave expansion on that quantity, we get this result, where again, we have a spherical Bessel function and two spherical harmonics for each I, where I is going up to n. N is the number of unit vector arguments we have in our function. Now, we can integrate each of these expressions against the spherical harmonic and set them equal to one another. In doing that, we end up with this equation here. Okay, so if we look at this expression, we can see that we have this integral over d omega p, which integrates over all the possible directions of p hat, the momentum or the dummy variable you have that's dual to r. And we define what we call the Gauss integral, where the Gauss integral is represented by this quantity g, and it's really an integral over n plus 1 spherical harmonics. Now, a couple of examples of the Gauss integral, if we evaluate it for n equals 2, this is what we get out of that. So we have two Wigner 3J symbols that couple the angular momentum, and we also have this coefficient c that depends on the angular momenta. If we evaluate the Gauss integral for n equals 3, it turns out that we can write it as a product of Gauss integrals for n equals 2. And this is what we find for the higher n equals 4, 5, etc. So in the expressions that I'm going to show on the following slides, they're going to have Wigner 3J symbols, which ultimately come from this Gauss integral, which is the integral of a product of spherical harmonics. Okay, so here is the relation we're starting with. If we replace this final d omega p integral with the Gauss integral, we get the second expression. And now let's remember that the unit vectors we started with had to have coupled to an isotropic mode in P before the integration over P. The way we can impose this condition is by setting L equal to 0, which implies that M is equal to 0. And if we do that to the second expression, we get this out of it. Now, something to note is that on the left-hand side, we have the 0th order spherical Bessel function. And we know that J0 is parity even. So this expression in the purple box can only produce even parity isotropic basis functions. Now, let's go through an example for n equals 2. If we start with our fundamental relation at the top, plug in n equals 2, and we can also replace this Gaunt integral with the n equals 2 case, which is shown here. If we combine these, we get this result out of it. So this shows that J0 of PR is the generating function for the n equals 2 isotropic basis functions. Now, let's recall from a handful of slides ago, I showed the n equals 2 isotropic basis function in the spherical harmonic basis. Let's compare that to our result from the previous slide. We see that both of them have a sum over m of two spherical harmonics, and we can use this to link the two expressions and set them equal to one another. After doing that, we end up with this result here. And this is our fundamental relation for generating the n equals 2 isotropic basis functions. Now, on the left side, we have a spherical Bessel function. On the right side, we also have two spherical Bessel functions. If you expand the spherical Bessels in a Taylor series, you can match the powers of P, R1, and R2 and pick out your isotropic basis function for specific L's. Now, you could do something similar to this for the n equals 3 case, but there's a caveat when you go to n equals 4 or higher, where you need to account for intermediate angular momenta. You need to account for these intermediate momenta because for n equals 4 and higher, you're not able to uniquely determine a rotationally invariant function without them. So in the n equals 4 example, we have L12, which couples L1 and L2. If we follow the same procedure as we did for the n equals 2 case, where we use the plane wave expansion two different ways and set those expressions equal to each other, we get this for the n equals 4 fundamental relation. Here, we see on the right side, we have a sum over L12, but we don't have any way to pick out a specific L12. So this approach doesn't work, and we have to slightly modify it. So first, for the n equals 4 case, let's define two vectors r and r prime that depend on the vectors that are the unit vector arguments of the n equals 4 isotropic function. Now, in the approach we showed earlier, each angular momentum was associated with a specific unit vector. So let's do that for the intermediate momentum we need for the n equals 4 case as well. So we associate L12 with some vector U12. And now we can again take two different versions of the plane wave expansion and set them equal to each other. This is the result for that approach. You can see we have Legendre polynomials, spherical Bessel functions, Wigner 3J symbols, and on the right side, the n equals 4 isotropic function. So again, if we use Taylor series to expand the functions on each side of this expression, we can match powers to pick out a specific isotropic function that we're looking for. Now, again, these two Wigner 3J symbols impose constraints on the angular momentum, and they impose that this actually is only a parity even function. It only produces the parity even isotropic basis functions. Great, but how do we obtain the odd parity isotropic functions, which are really what we want when we're doing a parity violation search? Well, n equals 3 and higher can have even or odd parity because n equals 3 corresponds to the 4 PCF. Now, if we look at the example for n equals 3, the simplest odd parity function we can have is P111. So let's think about how we can use this P111 to produce the odd parity functions. If we take the product of the lowest order odd parity function, P111, with some arbitrary even parity function, we can use the linearization identity for two isotropic functions, which is given in this first line here, where g is the Gaunt integral. If we do this, P111 acts as an operator similar to the raising and lowering operators in quantum mechanics, and it will convert the even parity function that you have into its nearest lying odd parity neighbor. So if we use our approach described earlier in this talk to generate the even parity functions, we can use a given odd parity function as an operator to obtain the odd parity functions. Okay, so how is this work actually useful? Well, it could enable us to develop a faster NPCF algorithm on the CPU. Now, I'm going to go through a brief overview of Encore, which is an algorithm for computing NPCFs using isotropic basis functions. So Encore takes a galaxy, bends its neighbors into spherical shells going out to some radius. And then on each shell, you have to determine a coefficient that we call ALM that encodes the angular dependence of the galaxies. Now, if you combine these coefficients and weight them appropriately by their angular momenta, you can project the NPCFs onto the isotropic functions. And to do this, you really need to go through this procedure for every primary and average the results. Okay. We know that Encore is efficient because it doesn't need to consider n-1 tuplets around each primary galaxy. The way that we obtain the harmonic expansion coefficients ALM about each primary scales as the number density times the maximum volume you're going out to. But since we need to do this for each galaxy, we also have to weight that scaling by the number of galaxies. So this is efficient, but we need to make sure that each expansion coefficient ALM is weighted in the correct way for each primary. That means that we have many different combinations of angular momenta that need to be summed over their projective quantum numbers. And this leads to a nested 9-level loop. Now, this loop can't be unwrapped or parallelized because of the selection rules on the angular momentum within it. Now, let's contrast that with what we could do with our generating function for the isotropic functions. Since the generating function allows the isotropic functions to be written in Cartesian form, we don't need to loop over the angular momenta or the corresponding projective quantum numbers. So if we use our generating functions to compute the isotropic functions, this could be less efficient in terms of flops, but since we're avoiding nested loops, this could be faster than Encore on the CPU. Now, I want to go through an example of how we would actually compute this. So I'll choose the isotropic function P112 just as an example. And we can see that there are different dot products that it depends on, but we'll just focus on the combination of these first two dot products here. If you take that, you can expand the dot products into the components of R1, R2, and R3. So you'll get 9 different terms in your sum. And here I'm just going to focus on this first term. If we take this, we know that we need to integrate the product of bin densities against the isotropic function in our calculations. And using the dot product expanded into its components, this integral turns into this expression here. Now, for a discrete density field, these integrals are actually sums over the galaxies and the shells. So this is efficient because just like Encore, it means we don't have to look at an n-1 tuplet around each primary in the sample. And just like Encore, each integral will have a scaling as the number density times the volume. Now, I just want to wrap up by going through a summary of what I've talked about today. So we often use the isotropic basis functions in their spherical harmonic decomposition to parameterize the endpoint correlation functions. What we've done is develop a generating function for these isotropic functions that allows us to easily obtain Cartesian expressions for the isotropic functions. And now the generating functions that we developed allow only the even parity functions to be generated. However, if you take the lowest odd parity function and multiply that with an even parity function, the odd function acts as an operator on the even function to produce the other odd parity functions, which are what we really need when we're doing a parity violation search. And finally, using the Cartesian expressions could allow us to develop a faster CPU algorithm to compute NPCFs.